So now we're going to take a look at moving to powers of tangent and secant. And again, why we're grouping these trig functions the way that we are is because of Pythagorean identities. So we grouped sine and cosine together because we've got that Pythagorean identity, sine squared plus cosine squared is equal to 1. And we have the similar secant squared of x is equal to tangent squared of x plus 1. So remember, both of these can be moved around, solved for whatever we want to be. We can solve for sine squared or tangent squared, whatever we need in the problem that we have. So again, there's a problem solving strategy that's laid out in OpenStax. I will also have a version of this in our notes, so you can kind of take a look and read through this, but we'll do a couple examples, and I think that will help figure out, sort of what it is that we want to do here. It's a little bit more complicated than the ones for sine and cosine, and it's because of what the derivatives are for tangent of x and secant of x. And it's again that idea that we're looking at trying to do a pretty simple substitution by making u either tangent or secant. Just tangent or just secant, not to a power or anything, just tangent or just secant. So we want to sort of have this strategy where we're looking at leaving or pulling aside in our integral either a secant squared or a secant times a tangent. So that's the idea of what we're looking for. And so for this one here, what I can do is, let's see, if j is even, that's exactly what we have here. J is the exponent on secant. So we're going to take secant here and we're going to pull two of those secants away. So we're going to pull away two of the secants. And that's because we're going to look at making our u tangent. And we're going to pull away two of them so that we've got a secant squared sitting kind of off to the side that we can use as our derivative of u. So we get tangent to the sixth times secant squared of x times secant squared of x. So that second one that I wrote there, that's the one I'm kind of viewing is going to sit there with the dx, and that's going to stay so that we can do substitution. Now this other one that we have, this secant squared, this one, we're going to use the Pythagorean identity to replace this. Let's see. So we've got secant squared of x is equal to tangent of x, tangent squared of x, plus 1. So let's see here. That's going to change our integral to still be tangent of x to the sixth. And then we'll have tangent squared of x plus 1, and then times that secant of x on the end, dx. So just to kind of underline what we've done here, the purple has replaced the underlined purple. And here, that sort of pink is that pink there. So now what we're going to do is our substitution. And we're going to have u being just tangent. And then du is equal to secant squared of x dx. So again, this is why we pulled that one out and aside so that we could do that substitution and the derivative of our u is sitting there for us. So now the substitution step, we're going to get u to the sixth and then times u squared plus 1 and then du. And this is much nicer than sort of the last one we had on the last video, because we just have to use the distributive property and we can multiply that through and we get 1/9 u to the 9th plus 1/7 u to the 7th. I was going to start writing tangent in there, but let's do that on this step right here. All right, there we go, and there's our solution. So again, we're using that Pythagorean identity that we've got, and we're using that to do our substitution. And again, we're trying to look for ways to leave a secant squared or a secant times tangent to pull that away so that we've got the derivative of our u in there so we can complete our substitution. So let's take a look at tangent to the fifth, secant to the seventh. So this one, if we go back up to sort of our strategy here, we've got that k is odd. That is the coefficient on tangent. So that's the situation we've got here. The suggestion there is to pull aside one of the tangents and one of the secants. So that's going to make our tangent to the fifth a tangent to the fourth, and our tangent to the seventh a tangent to the sixth. So we're just pulling those off of there so that right here we've got the derivative of u equaling secant. So that tells us our goal over here is to get this all in terms of secant. So we can do that again with that Pythagorean identity. We can take this one right here and rewrite it because we want to get rid of these tangents. So if we subtract 1 from both sides, we get secant squared of x minus 1 is equal to tangent squared of x. So let's see here. Now we've got this tangent to the fourth. Remember, that's this tangent squared. So that tangent to the fourth, maybe we'll take this little step here to rewrite that as tangent squared being squared. Secant to the sixth. And then our tangent, secant, it's like we're making this worse and worse, writing it longer and longer, but it's for a reason. It's to help make that derivative easy for us to take, or integral, sorry, easy for us to take. It's a little hard when we're doing both of those things in one problem. Okay, so now we've got everything that's not this part right here, that's our derivative that we set aside. Everything else is in terms of secant, so now we can do our substitution. U is going to be secant of x. So du is tangent of x, secant of x, dx. And so again, that's exactly why we left that sitting there. So it would be there for us to do the substitution. And we're going to get the integral of u squared minus 1 squared, u to the sixth, du. So similar to what we did in the last video, I've got to take that u squared minus 1 squared times u to the sixth, and we've got to multiply this out. So I will save us a little bit and tell us that this is going to give us u to the 10th minus 2u to the 8th plus u to the 6th. That's what you get from FOILing all of that out and using the distributive property. So that we've just got a polynomial, and that really is the goal with all of these, is to leave this with a polynomial that we know how to take the integral of. And yeah, we get sort of these ugly coefficients, but that's okay. We just have to then go secant to the 11th of x minus 2 ninths secant to the 9th plus 1/7 secant to the 7th of x plus c. There, we made it.